Today we're going to be looking at internal forces and moments. Later in this video we're going to be doing example problems to help practice these concepts. So we're going to start off by talking about the basics of force-couple interaction. Now the first thing we're going to talk about is force transmissibility. Now what this is if we have a force placed here on this hexagon, and we have the force's line of action, we can move that force anywhere along that line of action without having to induce a moment. Now this also applies for a system of many forces, such as this wedge here, with all of the red forces on the bottom side of the wedge. And we can move all of these forces to the top side of the wedge without inducing a moment. So what about the couple side of things? Now if we want to move the couple to a different location, we can do that fairly easily. So we have our couple in the bottom left of the hexagon here, and we can move it to the top portion of the hexagon, or even the bottom right portion of the hexagon, without having to compensate for that movement. All locations are equal for the couple. Now let's put both ideas together. Now we'll have a force couple system. So as you can see here, we have our hexagon once again, and now we're going to place a force on the bottom portion of the hexagon. Now this can move along its line of action without having to compensate for a moment, but if we move it off its line of action, we will have an induced moment in the clockwise direction. Now we want to be able to compensate for this to balance everything correctly. So this is the location of the original force. As you can see, it's moved to the upper right. Now, we want to first balance the force, so we put an equal and opposite force in red, going the opposite direction of the green arrow. So that's done. But now, we also need to balance the moment. Now this is done by the placement of the red arrow, which is at the same perpendicular distance, d, as the green arrow. Now, because of this has the same moment arm, and therefore creates the same moment, but in the opposite direction. So this is shown by the orange couple you see here. Now, both the forces and moments are balanced, and we are done. Let's apply these concepts to solve a basic problem. So right here we have an L-beam, measured as such. We have two 50-pound forces directly opposite each other. Now we're going to take a cut at this location and examine the top piece and the bottom piece individually to examine the internal forces and moments. So this will be the orange area and the green area shown. And then we separate the 50 pounds into its horizontal and vertical components, shown here. So let's take a look at the bottom piece first. So once again, here are the forces from the previous slide, and the green portion, that is the bottom piece we're looking at. Now, we're going to move the forces from the other side to that location. Now by moving that 40-pound force, we've induced a 120-pound-inch moment, shown there. And then by moving the 30-pound force, we have a 60-pound-inch moment, with calculations shown on the right. Now we can consolidate these into an overall 60-pound-inch moment going counterclockwise, as shown there by the purple arrow. So we can do the same thing for the top piece in orange here. So the green arrows are the forces that were placed on the bottom piece, and we're going to move those to the cut line. So the first thing we'll do is move the 40-pound force along its line of action to the cut line, meaning no induced moment is created. And then we're going to move the 30-pound force to the cut line, but since we moved it perpendicular to its line of action, we will have to have a moment to compensate. So we moved it at 2 inches from its line of action, and it's 30 pounds, so because of that, it's simply the force times the distance to get a moment, which is 30 pounds times 2 inches, which gives a reaction moment of 60 pound-inches at that location. So here we have our second example. This time we have a singular bar, just a straight bar with 2 holes in it for where the pins would go. And on these pins we have the forces shown as such. We have on the bottom left a 10-pound force going to the left, a 40-pound force going upwards. In the middle of the beam we have 80 pounds going to the right, and at the top right of the beam we have 70 pounds going to the left and 40 pounds going downward. Now like the previous problem, we're going to make a cut in the bar, and then we're going to separate it into 2 regions. Now for this problem we're only going to look at the orange section that you can see there. What we want to do is move the green forces, the 10-pound force and 40-pound force, to the cut. So we're going to start by moving the 10-pound force as shown. Now since we moved it off its line of action, we have to compensate with a moment. So that calculation is shown to the right, so it's 10 pounds moved 1 inch, which will create a moment of 10 pound-inches. There we are, now we have that. Now next, we want to move our 40-pound force. Now it is also moved off its line of action, so we have to have a moment reaction for that. So once again, the calculation is shown to the right. We have 40 pounds moved by 0.75 inches, so that creates a moment of 30 pound-inches. Now that we know the forces at the cut, we'd like to transform them into the axial and shear directions so we can know what the shear forces are across the face of the cut, as well as whether the member is in compression or tension. So currently we're in the vertical horizontal coordinate system, and we have our forces shown as such in the red, but we'd like to transform them into the shear and axial direction shown in blue. Now we know the sine and cosine of the angle between the vertical and horizontal coordinate system and the shear and axial coordinate system, shown here. And we can use this to calculate what the components of the 40-pound and 10-pound forces are in the shear and axial directions. So, once we do that, we find that there will be a 26-pound compression force in the axial direction and a 32-pound shear force in the positive direction, shown as such. Now that we've made the transformation, we can now superimpose those results onto the final product. So once again, we see our bar with our forces, the 70 pounds to the left, 40 pounds downward, and 80 pounds to the right, as well as our 10 pound-inch moment and our 30 pound-inch moment. And now we put our 32-pound shear force and 26-pound compression force on the cut. Now we can consolidate the 30-pound and 10-pound-inch moments into a single 40-pound-inch moment, as shown. And in summary, we once again have 32 pounds in shear force across the cut, 26 pounds in axial compression, and 40 pound-inches in bending at the cut. Now this will be our third example, and for this one we have a 3D problem. So we have a pipe coming out of a brick wall here, with the local coordinate system shown in orange near the wall. And we have two forces this time. We have a 100-pound force at 45 degrees to the I direction, and a 250-pound force at 30 degrees from the J direction. We're going to start by taking a look at the forces. Now, our cut is at the wall, so we want to be able to find what the reaction is at that point, so our reaction at the wall. We're going to start by decomposing the 100-pound force and 250-pound force into their I, J, and K components. Now we're going to start with the 100-pound force at 45 degrees from the I axis. So, using the cosine and sine relations, we can find that there will be a 70.7 pound force in the K direction and a 70.7 pound force in the minus I direction due to the 100-pound force. Now, we can also do this for the 250-pound force, and using the same cosine and sine relations, we find that there'll be a 216-pound force in the J direction and a 125-pound force in the minus K direction. Now, what we can do next is place equal and opposite reactions at the wall, as shown, and then we can consolidate the K direction forces into an overall 54.3 pound force in the positive K direction. Now we're going to determine the moment reaction at the wall. So once again, here's our pipe with the forces shown by the orange arrows, and we're going to use the equation R cross F to determine the moment reactions. Once again, moving forces off the axes generates moments, and we're going to use that to be able to solve the problem. So our first vector pair is R1 and F1. Now, R1 is the distance vector from the cut to the point where the forces are located, and F1 is the force vector. That is shown there. So R1 is 0 inches in the I direction, 9 inches in the J direction, and 0 inches in the K direction. F1 is composed of minus 70.7 pound in the minus I direction, 0 pounds in the J direction, and 70.7 pounds in the K direction. Now, similar to this first vector pair, we have a second vector pair, which is R2 and F2. Those components are shown in the bottom left. Now, once we have these, we can calculate R1 cross F1 and R2 cross F2, which gives us the moments shown on the right-hand side of the equation. Now, once we have both sets of vectors, we can then take those and join them into the total moment, which is shown on the far right, of minus 214.2 pound-inches about the I, minus 750 pound-inches about the J, and minus 662.7 pound-inches about the K. Now, in order to find the actual reaction, we simply find the negative of that vector, shown there. So now we've determined the reaction forces and moments, what happens to the bar? So we know our equivalent moment on the bar, so we can look at the moments about each direction to figure out what happens. So we're going to first look at the moment about the I direction. So this will be looking at the side of the bar. Now beforehand you can see the picture in blue there. Now after the forces are applied, due to the bending moment of minus 214.2 pound-inches, it will bend downwards like that. Now if you look at the J direction, we have the bar at this perspective looking down the bar towards the wall, and after the moment is applied we see a twisting motion like this. Now finally, if we look about the K direction, so that will be looking at the top of the bar from the top of the wall, after the moment is applied it'll bend towards the right. Now we've used forces and force couple systems to be able to evaluate several problems, and now you can use it on your own to evaluate problems of your own.